Okay, so last time we talked about potential, potential difference, things like that from a uniform field between two plates. Right, we had a V1, a V2, we had some distance, and we calculated the potential difference was the potential energy over the charge. The potential energy was the work done, which was the force times the distance. So we had QE was the force times the distance, and then that's divided by Q. So I don't know that we wrote it last time, but the change in potential just ended up being cancel those out, E times D, right? And so that was for the special case where we have a nice uniform field between parallel plates and all that kind of stuff. Today we're doing point charges, all right? So point charges have their own formula for potential, right? It's related to, it's still, potential is potential energy over charge, but the electric field and the shape of the electric field is different, so we'll have a different expression for the electric potential. And so for this problem, we want to just know what is the electric potential at point P. So we have three different point charges, all right? And we want to know what is the potential, what is the voltage right here at point P, okay? And so for this, just like the other things where we had multiple charges and we wanted to calculate what the force was, what the electric field was, we can use the idea of superposition. So we're going to say that V total is just V1 plus V2 plus V3. All right. The nice thing about energy is that it's not a vector, right? So we don't have to keep track of the vector parts of it. We can just calculate the potentials directly, add them up as just regular old numbers, scalars, right? And so, yes, we got these numbered, and so we need the point charge potential equation. So the potential at a point charge, again, this is now assuming that it's zero. The potential energy zero is infinitely far away. So the potential at the point charge is just KQ over R. Right? So again, very similar to all of our, force was KQQ over R squared. Field was KQ over R squared. Now we've lost an R in the bottom, so the potential is just KQ over R, right? Because of of the because of the because of energy being force times the distance, right? And so so we're multiplying by one of these r's is like the distance, and so that gets rid of one of the r's from the bottom. Okay, so let's go ahead and plug these in. So do we need some steps? Basically the steps will be like always, get a good diagram, know what we're talking about, and then for these, saying a superposition idea, find the v from each one. You don't have to make them vectors, so just find the v's and then add them up. All right, so, and maybe we can just do it all in one equation. Oh, let's just do it separately. So v1 is going to be kq1 over r1. All right. K is same old K, 8.9876, 10 to the positive 9 Newton meters squared per Coulomb squared. Q1 is here, 1 nanocoulomb, 1 times 10 to the negative 9 coulombs. And then R1. R is just like, is the distance from the charge to wherever we're looking for, trying to find the potential. So in this case, it's 1, 2, 3, 4. 4, we'll just say these are centimeters as usual. So 0.04 meters. Alrighty. And so we get a mess of units here, but we've got everything in standard units, so I don't think I'm going to take the time to go through and convert it to joules and then joules per coulomb. Anyway, when we put it all together, we can, since we put in everything in the correct standard units, we will get volts as our output for V1. So V1 is 8.9876 E9 times 1 V times 1e negative 9 divided by 0.04. Okay. Ooh, all right. Well, 224.7 volts. Kind of a high voltage, but we'll go with it. I'm just making up numbers. V2, same process. V2, KQ2 over R2. In this case, K still the same, but when we are doing potential, we do need to keep the sign on our Q's. All right, so it's not a vector, but it does have positive and negative. It can't increase energy or decrease energy. Negative charges make different things happen in the field around them than the positive charges do, right? So this is a negative charge, so we need a negative 2 times 10 to the negative 9 coulombs. And then R2 is here, R2, right, whereas this was R1. So R2, we need to do a little triangle stuff. So we got one side, 1, 2, 3, 4, 5. One side is 5 centimeters and the other one is 4. So just kind of as a side note here, R2 squared, looking at this triangle, C squared is A squared plus B squared. So R2 squared is 0.05 squared plus 0.04 squared. All right, so we're going to put under here square root of 0.05 squared plus 0.04 squared to get R2 by itself. So V2 then, 8.9876 E9 times negative 2E negative 9 divided by square root of 0.05 squared plus 0.04 squared. That looks like it did pretty well. Yeah, looks okay. So minus 280.7 volts. Okay, is what V2 is going to do to that point P's voltage potential. And then V3. Again, same formula. KQ3 over R3. K, 8.9876, 10 to the 9th. Q3 is positive again, 3 times 10 to the 9th. Negative 9th, nanos. And then R3 is just the distance from that point to 0.3, so that's just the horizontal 1, 2, 3, 4, 5. So 0.05 meters. No squares. Oh, no squares. This is potential. Squares are for field and force. Okay. So we get 8.9876 E9 times 3E negative 9 divided by 0.05. Ooh, there's a big one. 539.3 volts. Positive because Q is positive. All right, so the potential, the total potential at point P is, add those up, so 224.7 minus 280.7 plus 539.3, all in volts. 224.7 minus 280.7 plus 539.3. 483 volts is the potential at point P. All right, I think that'll do it. We'll stop there.